You know, every so often, a technology jumps straight out of science fiction and, well, lands right in the middle of business strategy meetings. We're talking about quantum computing today. For ages, it felt purely theoretical, right? But now, it's shaping up to be a real source of competitive advantage. The tricky part, unlike, say, AI, most people can't quite explain what it is. So our mission in this deep dive is to fix that. We want to unpack the basics, the physics behind its incredible power, and maybe most importantly, give you a solid framework, this one's from MIT and Accenture, to figure out when quantum computing might actually help your business, and frankly, when it's just not the right tool.
That's a crucial point, because quantum computing isn't just about doing current tasks faster. It's a fundamentally different approach. It uses quantum mechanics, how things work at the tiniest scales, to tackle problems that are basically impossible for today's best supercomputers. Think about optimizing a global supply chain with millions of variables, or simulating complex molecules for drug discovery, problems with just astronomical numbers of possibilities.
Right. And that difference starts at the very core, with the basic unit of information. We all know classical computers use bits, zeros, or ones. Simple switch.
Exactly. But the quantum bit, the qubit, that replaces the switch with something more like a dimmer, or maybe a spectrum of possibilities. It taps into these unique quantum effects, superposition and entanglement, giving it access to, well, mathematical shortcuts that classical machines just don't have.
Okay, let's dive into that qubit then, because that's where the magic, or maybe the math, really starts. How does adding uncertainty being both 0 and 1 actually make it more powerful?
That's superposition. So instead of being definitely 0 or definitely 1, a qubit exists in a combination of both states at the same time until you measure it. Think of it like a coin spinning in the air. It's neither heads nor tails until it lands. While it's spinning, it represents both possibilities.
The spinning coin.
Yeah.
Okay, so one qubit holds two possibilities. How do we get to the kind of exponential scaling everyone mentions? That sounds like more than just spinning coins.
That's entanglement. This is where it gets, well, almost weird, but incredibly powerful. Entanglement links qubits together. Their fates are intertwined, you could say. If you know the state of one entangled qubit, you instantly know the state of its partner, no matter how far apart they are.
This spooky action at a distance Einstein talked about.
That's the one. And because of this linkage, when you entangle qubits, their combined computational space grows exponentially. So 2 entangled qubits in superposition can represent 4 states simultaneously. 3 qubits handle 8 states. You get to, say, 100 entangled qubits, and you're dealing with 2 to the power of 100 possible states. That's an absolutely enormous number. More states than atoms in the known universe, basically.
Wow. Okay, so it can explore this vast landscape of possibilities all at once.
Effectively, yes. That's how it can tackle certain problems in minutes or hours that would take the best classical supercomputers thousands, maybe millions of years.
But it's not just blindly checking everything, is it? I heard about something called interference playing a role. Like it guides the calculation.
Exactly. Interference is key. You can think of the possibilities in superposition as waves. We design quantum algorithms so that the waves corresponding to wrong answers cancel each other out, destructive interference. And the waves for the right answer reinforce each other, constructive interference. So it guides the computation toward the correct solution much faster. It's finding the signal in the noise, in a way.
That sounds incredibly sensitive, though. Keeping those waves perfectly aligned must be tough.
It is extremely tough. And that brings us to a major challenge: decoherence. Decoherence is basically anything in the environment, tiny vibrations, heat, any interaction really that causes the qubit to lose its quantum weirdness and collapse back into behaving like a simple classical bit, a 0 or a 1.
A spinning coin lands before you want it to.
Precisely. And controlling decoherence is why quantum computers need such extreme conditions like cooling near absolute 0 and very careful shielding. It's a massive engineering hurdle.
Okay, so we have the quantum principles, superposition, entanglement, interference, and the big challenge, decoherence. But let's get practical. Before businesses invest millions, they need to know, is this quantum tortoise actually going to beat the classical hare for my specific problem? Not just some theoretical problem, but my supply chain, my financial model.
That is the million-dollar question, maybe billion-dollar question. And that MIT Accenture framework you mentioned tackles exactly this. They use that tortoise and hare analogy.
Right. Tell us about that race.
Okay, so the classical computer is the hare. It's incredibly fast at each individual step, each calculation, blazing fast processor speed. But for certain complex problems, the method it has to use, the algorithm, is very inefficient. It takes a really long, winding road with many, many steps.
Lots of calculations per second, but a huge number of calculations needed.
Exactly. Now, the quantum computer is the tortoise. Its individual operations, its clock speed, if you like, are actually much slower than the hare's. But thanks to superposition and entanglement, it can use algorithms that take a fundamentally shorter path, a much more direct route to the answer.
So the crucial thing is, the race needs to be long enough for the tortoise's better route to actually matter more than the hare's raw speed.
Precisely. For many typical business problems, even complex spreadsheets or standard database queries, the classical hare wins easily. The race is too short, its speed gets it there faster. Quantum computing really shines only when the problem is so complex the classical route becomes astronomically long. That's when the quantum shortcut provides a real advantage.
Like those examples you gave, massive logistics, materials science, maybe drug discovery, certain types of financial risk.
Yes, problems where the number of variables or interactions grows exponentially. Simulating how molecules behave, optimizing thousands of interacting variables on a factory floor, or analyzing incredibly complex financial derivatives, that's the sweet spot.
Okay, so for leaders thinking about this, we need to differentiate. There's quantum advantage, the idea of solving something no classical computer could ever solve. Maybe that's far off for many. But then there's quantum economic advantage. That sounds much more relevant day to day. What's the difference?
That's a really important distinction for practical investment decisions. Quantum advantage is the ultimate scientific goal, sure, but why is economic advantage the key metric? Isn't just solving it enough?
Well, think about it. If a quantum computer can solve your problem in an hour, but a classical supercomputer cluster could also solve it in an hour, maybe even two, and that classical cluster costs, say, 10 times less to build and run than the quantum computer, then you haven't actually gained an economic advantage, have you?
Ah, I see. So quantum economic advantage means the quantum solution is faster or better than a comparably priced classical solution. It's about value for money, essentially.
Exactly. You need two things. First, feasibility. A quantum computer powerful enough to run your specific algorithm actually needs to exist. That's still a big if for many complex problems. And second, algorithmic advantage proof that the quantum approach is genuinely faster or provide a better solution than the best similarly priced classical method. Both have to be true.
And companies are betting on this future feasibility and advantage now. We're seeing significant investments already, some firms spending over $15 million a year exploring this. McKinsey projects maybe 5,000 quantum computers operational by 2030, but, and this is a big but, for the really complex, game-changing problems, the kind needing full fault tolerance, we might be looking at 2035 or even later for the hardware and software to be truly ready.
It's a long game.
Yeah.
And to really nail down how these machines tackle problems classical ones can't, let's use an analogy. I like the light switch game example.
Yes, that's a great way to visualize optimization problems, which are central to what quantum computers are good at. Imagine you have a room, or maybe a whole building, filled with lights, which say 500 of them, and they're all interconnected in complex ways. Flipping one switch might affect the cost or energy associated with several others.
Okay, like some configurations are cheaper or more stable than others.
Exactly. Each switch might have its own preference, a bias, to be on or O-off F, and each pair of connected switches might have a preference for being in the same state, both on or both O-off or opposite states.
And the goal is to find the single combination of ONs and OFFs across all 500 switches that results in the absolute lowest total cost or energy for the whole system.
That's the optimization challenge.
And the problem is, with 500 switches, checking every single combination, well, 2 to the power of 500 possibilities.
Yeah.
It's just impossible classically. You need more time than the age of the universe.
Literally impossible. But the quantum computer takes a different route. You start by putting all the qubits representing the switches into superposition. So effectively, all switches are both on and off simultaneously. The system explores all configurations at once.
The entire possibility space.
Yes. Then you program the computer by encoding those biases and connection preferences, the rules of the game, the energy landscape of the problem, and then you slowly turn off the quantum effects, gently nudging the system out of superposition. You might also slowly turn up the influence of the problem's constraints, the biases and connections.
Like letting the spinning coins slowly wobble and settle?
Kind of. As the system loses its quantumness, it naturally seeks out and settles into the state with the very lowest energy, which, by design, corresponds to the optimal on-off configuration of the switches. the solution to your optimization problem.
So it finds the lowest point in that energy landscape without having to check every peak and valley along the way. That's clever.
It's incredibly powerful for these kinds of optimization tasks. And that ability is exactly why people are so excited about quantum machine learning or QML. Think about training an AI. It's often about finding the optimal settings or weights within a complex model to best match the training data. That's an optimization problem.
So quantum could potentially speed up finding those optimal settings for really complex AI models, for things like image recognition or understanding natural language.
That's the hope. You show the quantum system labeled examples. This image is an apple, this one is a raspberry. And the system adjusts its internal energy program, those switch biases and connections, metaphorically speaking, until it correctly classifies the examples by settling into the right low-energy states. It effectively programs itself through optimization.
And another interesting thing is the output, right? Classical computers usually give one answer. Quantum computers. They're probabilistic.
Yes, that's a key difference. If you run the same quantum computation multiple times, you might get slightly different results centered around the most probable, lowest energy answer. It gives you a probability distribution of possible solutions.
And that uncertainty isn't necessarily bad.
Not at all. Sometimes that uncertainty is the valuable information. Imagine that image you fed it actually had both apples and raspberries blurred together. If the quantum computer comes back saying, well, 50% of the time I think it's an apple, 50% I think it's a raspberry, that accurately reflects the ambiguity in the input data itself. That's really useful information that a single best guess answer might hide.
Okay, the potential seems huge, especially for optimization and maybe machine learning. But let's talk about the present-day hurdles. The hardware sounds like a beast.
It really is. Scaling up is challenge number one. We need to get from hundreds or thousands of qubits today to potentially millions for fault-tolerant computing. Google's aiming for a 1 million qubit machine by 2030, which is ambitious. And then there's the error correction, dealing with decoherence. Qubits are incredibly fragile. Noise is a constant battle.
Which is why they need those massive refrigerators, right?
Yeah.
Size of a car, cooled to near absolute zero.
Exactly. Keeping the environment stable enough is a monumental engineering task. You need sophisticated cryogenics, shielding. It's complex and expensive.
So error correction isn't just a software problem. It's deeply tied to the hardware quality.
Yeah.
You actually need many physical qubits just to represent one stable logical qubit.
Correct. Fault-tolerant quantum computing requires encoding the information across many physical qubits to detect and correct errors caused by decoherence. It significantly increases the required qubit count. That's a huge area of research and development right now.
Okay, hardware is tough. What else? You mentioned investment is happening, but is the talent there? Can we actually find people to build and run these things and figure out how businesses can use them?
That's perhaps the most immediate bottleneck. The talent gap is severe. McKinsey estimates that by 2025, maybe fewer than half of the open quantum computing jobs will actually be filled. There's something like only one qualified candidate for every 3 quantum job openings right now.
Wow, 1 in 3. And the field is only expected to grow.
Exactly. We desperately need more people trained in quantum physics, quantum algorithms, software, hardware engineering, and crucially, people who can translate between the quantum science and actual business problems.
Despite these challenges, hardware, errors, talent, we're making progress. You mentioned milestones. We hit quantum utility recently.
Yes, around 2023. That means quantum systems started providing reliable solutions to certain problems that were genuinely hard for even large classical simulations, maybe not faster or cheaper yet, but demonstrating real capability on problems beyond brute force.
And the next big one is quantum advantage. Expected when?
The hope or expectation is maybe late 2026, give or take. That's the point where a quantum computer demonstrably solves a meaningful problem better, faster, or cheaper than any known classical method. That'll be a major turning point.
And even then, it's not like quantum computers will replace classical ones entirely, right?
Yeah.
It's more of a partnership.
Absolutely. The vision is hybrid computation. Use classical supercomputers for what they're good at managing huge data sets, input-output, running parts of the problem that aren't quantum-suited. Then you call on the specialized quantum processor for the really complex core calculation, the optimization or simulation part that needs that quantum power. They'll work together.
So wrapping this up, the key takeaway seems to be, quantum computing isn't just faster, it's a different way of computing altogether. It leverages superposition and entanglement to turn these impossibly large exponential problems into solvable optimization tasks, finding the lowest energy state.
Exactly. And the impact will be profound across many fields. Pharmaceuticals designing new drugs by simulating molecules with incredible accuracy. Green technology discovering new catalysts for things like carbon capture or creating better batteries. And of course, cybersecurity. Shor's algorithm, a quantum algorithm, can break much of today's standard encryption. That threat alone is driving a huge push towards developing quantum resistant cryptography now.
So here's the final thought for everyone listening. The potential value here is estimated at something like $1.3 trillion by 2035. Huge numbers. But we have this critical talent shortage. Only one qualified person for every 3 jobs. Thinking about the recent AI boom and how quickly companies had to adapt, how crucial is it right now for organizations to not just track quantum, but to actively start defining where it might fit their specific needs? And maybe more importantly, investing early in finding or training those translators, the people who can bridge the deep science and the practical business applications to make sure they're ready to actually capture some of that trillion-dollar advantage when it fully arrives. That seems like the strategic imperative today. Thanks for joining us for this deep dive.